Hello, everyone. Today my topic is van der Waal equation, and my presentation has three parts. The first part is introduction or review of van der Waal equations. So, I believe you guys are familiar with ideal gas law. In this law, we ignore the intermolecular force between gas particles, and we think the gas molecules are not take up any spaces. It means their volumes are all zero. However, this kind of situation is impossible because the gas around us are matters. Matter takes up space, and there are strong interactions among them, uh, although we cannot see. So these two elements are very important on influencing the gas different gas different is different traits. So the famous scientist Van der Waal revised the PV-nRT to this equation. So compared to the ideal gas law equation, there are several new symbols. So the n squared divided v squared is the concentration squared. You can also think this a density because n is a mole and v is a volume. And A is a constant related to the intermolecular force or attractive force between real molecules. N is number of moles. B is a volume correction constant related to blah blah blah. And in the next part, I will show my process so you can better understand what A and B stands for. So let's quickly move on to the part B. So today, my my in-depth topic is to show you guys the researching process about what A and B in van der Waal equation stands for. So the volume, I said before, in ideal gas law state, we ignore the size of gas molecules. It will cause the volume for molecule free motion is decreasing. So we can write the equation as V ideal is equal to V minus B. The V ideal is is in ideal gas law, and this V is in van der Waal equations. The B I will talk in the next part. So, and the intermolecular force. So it's clear that between two gas molecules, there are attractions between them. The distance d and the attractions F1 and F2. This distance is increasing. Their attractions is decreasing. D is increasing and the attraction is decreasing and increasing, but the attraction is still exists and will not be zero. It's always larger than zero, which means it is a it's an important trait we need to consider in the real gas model. So, and we can give that. So let's talk about the A. About A is intermolecular force first. So you can see in a closed container there's a molecule here, and this molecule is attracted by other molecules, and F1, F2, F3, F4, F5, F6, F7, F9. But although there are many forces, each of the directions of the force is cancelled. So the net force on this molecule is zero. But this is just what ideal gas laws considers for. I think they ignored one thing is the molecules close to the wall of the container. You can see this molecule. It cancels in the F1 and the F3 direction, but in F2 there are no force which cancels F2, so it creates a net unbalanced force on this molecule. So we can understand that the F2 wants to put this molecule living away from the wall. So what it causes? It causes the molecule's pressure on the wall decreasing, and we called this decreasing pressure by Pj. So we can write it as the P ideal is P plus Aj, and P ideal is in the ideal gas law equation. The P is in the van der Waal equation. And since in the two pictures there are only one molecules we find, so we can write van der Waal equations like that, and the n is equal to 1, so we don't write n here. So let's move on to the let's move on more about the Pg. Sorry, it's not Pi, it's Pg. There's one molecule here, but it's also one molecules around him. So more molecules around this molecule, and more dense these molecules are, it will cause the force on this molecule become more and more larger. So it is closely related to the density, and this is a constant. And in this diagram, you can see that there are several molecules which gives the pressure on the wall, and we know if the molecule are more dense, the pressure will increase. So pressure is closely related to the density 2, and the total force by combining first and the second diagram, we know the total force on this is closely related to the K1 K2 n square by multiplying these two. So we know the Pg, the pressure on the wall, is equal to the F, force on the molecule, related to this, related to this, and related to this. So what NV? N is number of the number, or can you say the moles of the molecule? V is the volume. So N is a constant because it stands for mole. It's a number. So we can write as this. So that's what A stands for. You can see that. Because in my reduction process I use only one molecule, so in this situation n is equal to 1, and that's what this. So let's move on to the volume about B. So what about B? Consider there are two molecules here, gas molecules here. They are 2D on my diagram, but they are 3D in the real situation. They're 3D, they're spheres, not circle. So imagine they are suppose the radius of them is all r, and the collision area of two is r. How to get the collision area of these two molecules? You can rotate my diagram around, and you will find that it is the collision area. The rotation area is also a circle. The circle's radius is 2r. So the volume of collision area is 4 to 3 pi 2r and 3 square. The volume, and we know the volume single molecule is 4 divided 3 pi r3. So we can find that by these two equations, we can find that the V collision area, the volume of collision, is equal to 8 multiply the volume of one molecule. And we'll find that in a closed container, suppose the container's volume is V container, the volume for one molecule is available for one molecule is V container. But if the second molecule wants to enter the container, it becomes V available for two. It becomes V subtract V collision. You may ask that why not V minus V molecule? Because I draw a diagram here. You can see that when you place the many circles or spheres together, there are still some blanks among each other, and these blanks take up the container space, but they cannot but the gas molecule cannot take this blank, but the blank take up the container space. So you can understand that this blank is just a waste. So 1 is container, 2 is V minus this 3, and we find a rule. So when the nth molecules enter the container, it is V minus n minus 1 V collision. And we want to find the average volume available for each molecule. So we plus 1, 2, 3 to n their available volume, and we divide n, and we find that the result is Weiran container subtract subtract 1 divide 2 V collision. Sorry, it's little unclear. It's collision. And in real situation, there are trillions of molecules in the container. So n minus 1 is nearly equal to n. So we can revise this equation as V container subtract n divide 2 V collision. And since we know that this V collision is equal to 8 V molecule, we can write as V subtract 4. It should be as V subtract 4 n. N is this n and V molecule. So we treated 4 n V molecule as B. N is the number of molecules, and Vm is volume for one molecule. So it is the total volume. So B is equal to 4 multiply total volume of molecules. So that's my resulting process for the definition of A and B and why they come from. So we find the van der Waals equation as this. It is one more van der Waals equation, and it's more molecules van der Waals equation, just like this. So let's move on. And you may familiar with these pictures on OnQ, and it can help you understand what I said before. So let's quickly move on to the final part, sample questions of van der Waals equations. So I give you a question to do. Use van der Waals equation to calculate the pressure exerted by 1 mole CO2 confined to a volume of 2L as 273K for CO2. A is equal to this, and B is equal to this. And this is my solving process. Sorry, it's a little unclear, but you can still see the data. Since we know the N, the volume, the temperature, the A and B, except P, so we can easily find the P by simplifying this van der Waals equation to find that in real gas law it states the P is equal to 10.1 bar, and I want to find more about this question. It means the result doesn't end here. I want to know which one, intermolecular force or the volume, plays a more important part influencing on the CO2. So it means I will treat this question in the ideal gas situation too. So we find in ideal gas law state the P is equal to 11.3 bar. To compare intermolecular force and volume's influence on CO2 pressure, include only B in van der Waals equation. We found P is equal to 11.7, and we'll find that if we only include B without A, it is 11.7, just 0.4 difference with the ideal gas law state. But if we include A and B, the P will have a 1.2 difference with ideal gas law. So that means the B plays a minor role and A plays an important role for CO2 pressure. It means intermolecular force is the main cause for departure of the real gas. And so this is all for my presentation. Thank you.